Hey everybody, this is the video detailing our project, the Math Homework Helper, which we designed for the Integrated Systems Design 2 class, Senior Design at Clemson University over the past 3 months. First, we're going to introduce the team members. Hi, my name is Charles Kowalski. I'm a computer engineer here at Clemson, and my future plans, I'm going to be going to Georgia Tech for a master's with a focus on VLSI. My main part of the project was working on the software and the overall final integration for the project.
Hi, my name is John. I'm a computer engineer at Clemson, and my future plans are to stay at Clemson for another year to get a master's. And I worked closely with Charles mainly on the software for this project.
Hello, my name is Thomas. I'm also a computer engineering major here at Clemson. I am pursuing a master's degree in mechatronics and robotics next year at Michigan, and my main part of the project involved the hardware design, focusing around the circuit design and CAD.
Hi, I'm Connor Witt. I am the lone electrical engineering major on this project. After I graduate, I will be moving to Charleston to work for DES. On this project, I focus mostly on assisting Thomas with the hardware design and CAD. Moving into our motivation for this project, we're seeing as education moves further online, access to personalized math help can be limited, and many of the online services that are available right now don't capture the hands-on, tactile learning approach that you see in the classroom. We wanted to create a device that is low cost and accessible for students K through 12 on their math journey.
So now moving into the definition for our project, we had a couple objectives we set out to accomplish from the start. And three of those here are that we wanted to be able to write on an 8x5 by 11 piece of paper and be able to solve any math problem using just a single button input. And then on top of that, we wanted our solution to be accurate 85% of the time on K through 12 mathematics. And we wanted the runtime for each of these problems to not exceed 60 seconds.
So moving on to the system overview, getting a high-level view of the actual solution. On the left in the orange box, you have the pen plotter, which represents the hardware and the mechanical system that we use to solve the problem. And then on the right, the green box is the Raspberry Pi 5, which is our main compute hardware. And on that is the large language model, the stroke parser, and the motion planner. The overall flow of the system starts in the top left with the camera. The camera takes an image of the question that the student is asking. That image is passed into the Raspberry Pi and processed via a large language model, which is offsite and it's queried using an API. That large language model provides a solution in the form of text, which is then passed into a Hershey text stroke parser. That module then passes the strokes required for that solution to the motion planner, and then the motion planner executes the solution using the stepper motors in the hardware to actually realize the text onto the paper.
Now we're going to discuss the electronics design for our project. So the main electronics platforms, as discussed before, we have the Raspberry Pi 5, and we also produce our own custom PCB to drive the stepper motor drivers, as well as other onboard hardware like limit switches and our servo motor. So you can see this on the top right. There's an image of the PCB file. Our project access the internet via Ethernet. So on this custom PCB, 12 volts was provided to the stepper motors, and we had a onboard buck converter that dropped this voltage down to 5 volts for the 5-volt pins on the stepper motor drivers and to control our servo and our limit switches.
All right, moving into the mechanical design of our system, we took a lot of inspiration from the Core XY theoretical design that is seen in a lot of 3D printer technology. This allows us to manipulate the main plate with two NEMA 17 stepper motors to essentially position our writing machine properly. In addition to that, we have a Z-axis controlled servo motor that when prompted, lowers and lifts the writing utensil. And on top of that, we also have included a human machine interface um, that has multiple LED indicators showing what status the machine is in, whether that be solving, writing, or an error occurred. And all of this, of course, is connected to the Raspberry Pi and custom PCB that was discussed earlier.
So now that we've covered the hardware, we're going to move on to the software. To start, we used object-oriented Python to write the software for this project, and we deployed that software on a Raspberry Pi 5. Within the Python files, we developed objects, and each object is responsible for a different subsystem of the project. This includes hardware handlers, a class that interacts with the OpenAI API, and then a class that handles the I/O for the project. To start at the top, we have the project controller, which uses all of the other classes to do the high-level actions of the project. The project controller interacts with the motion planner, the image prompt solver, and the plotter I/O controller.
Now that Charles has gone over the object hierarchy, I'll discuss the software flow. Inside of our main program, we instantiate each of the classes that Charles just mentioned, and then we call each of these objects when necessary to accomplish our program. First, we wait for the start button to be pressed, which triggers the start of the program. When the start button is received, we take a picture with the webcam and we trigger the light on the LED I/O box saying the solving process has begun. This picture is passed to the LLM, which we use GPT-4o using the OpenAI API, and we prepend a system prompt to this LLM query. We receive the LLM query in string format, and we take this string and pass it to our Hershey text stroke parser, which splits up each of the characters into different character strokes. Once we receive these character strokes, we pass it to our motion planner object, which breaks these down into the coordinates needed for each character and sends these to PWM controllers. Then the process goes through a writing process, and we trigger again the writing light and turn off the solving light. And we write each character one at a time until the string has been completed, and this triggers the light to turn off and the main program to cycle back to wait for the start button again.
All right, so moving on to our performance analysis section of our presentation. Overall, we successfully met and exceeded the original design goals for the speed and accuracy parameters of our project. We were able to get the system to solve at a 90% accuracy on grade school math and basic calculus, and we were able to also meet the power requirements and we're able to solve the problems in the designated workspace. We ran into problems, however, with some of the actual handwriting reliability. We faced many issues in terms of system sag, where it was hard to get the handwriting utensil to actually consistently write legible characters. We were able to minimize this through a variety of techniques, but it was still a problem to the end. We also suffered a little bit of mechanical problems in relation to the servo motor, which were extremely hard to diagnose, but overall, they did not make the system unusable by any means.
So to conclude, overall, we achieved our system goals while staying under budget and on schedule. We did the whole project for just under $250, and it took one semester or about 3 months. Overall, we learned important engineering and project management concepts. On the software side, we learned about object-oriented Python programming and low-level hardware control. And then on the hardware side, we learned a lot about custom PCB design and the wiring up of the systems. Additionally, we learned project management concepts like project planning, Gantt charts, task delegation, and overall how to make a complex system come to life with multiple engineers working on the project simultaneously. Future work includes hyperparameter optimization. OpenAI offers the option for you to tune how often your model will make its own decisions, how random the output will be, and we would like to decrease that because we had some issues with keeping the output consistent for the same question. We'd also like to look into frame strengthening to hopefully counteract some of that mechanical sag and hopefully strengthen the system a bit more whether that's a different filament for the 3D printed parts or moving away from 3D printed parts entirely. That is an option for future effort. And additionally, we would like to support additional glyphs, meaning fractions, advanced math symbols. Right now, the system cannot do fractions. It will just put a / in between the two numbers, but we'd like to have that actually do a real fraction, so numbers on top of each other. And then advanced math symbols, think integers, or excuse me, integrals, um, other Greek letters, and things of that sort, so we can better represent the problems that the students are looking to solve. But overall, we were successful in our goal, and we met and exceeded our expectations for the system. So that's the project. We really want to, as a team, give a massive thanks to Dr. Raza and the Clemson ECE department. Throughout the course of the semester, Dr. Raza has been a huge resource, mentor, and professor to us. He's always willing to give a hand, and he's always willing to he's coming around asking if we need anything, and he really tries hard to make this a seamless process. And he's taught us so much over the past four months. And also to the Clemson ECE department, this is the culmination of the past 4 years of learning for us, and really we couldn't have done it without the amazing professors, staff, and honestly peers in the Clemson ECE department. And just super happy to be a part of the Clemson family and to see this through. So thank you very much.